Yeah, so, all right, let me share screen real fast. There's that vector handout. That's still right here. And that's what we're gonna use. You started looking at it on Friday, right? Switch the share up. Switch to the actual. Right. So we went through kind of page 1 on Friday quickly. And then we're going to start page 2 today, which is the dot product stuff. But let me just say a few words about these problems. Yeah, I'm going to go to the board and say some things about 3, and 4 through 6, just for a few minutes. Then we'll look at the top of page 2, just to talk about what the dot product is a little bit, and then we'll break into groups. Exciting stuff. All right. So one thing is, yeah, I think I said this very, very briefly at the end of class. We were out of time, and I talked to some groups about it. But I think there's an important, one reason I put this on the problems to do is that I think it's important to notice that these are quote unquote displacement vectors, that it's really about the tip to tail difference, not about where the tail is. That here, A, B, and C are actually all the exact same vector. Because I know I've seen students before think of B as like, they almost want B to be D, like coming from the origin of that to the tip, right? But it really just matters that, I did that right, A equals B equals C. And I think we said that was just 3K. So I mean, you could just say 3K, or you could say 0I plus 0J plus 3K, however you want to say it. Right? So it's just, there's no change in X, there's no change in Y, and there's just a change in Z. Okay, and then the rest you can just sort of read stuff off, right? Like, can someone tell me what D is? Volunteers. I see it. Yeah. Yeah, there's no J component, there's no Y component, right? So, but it goes 2 units in the X direction and 3 units again in the Z direction, right? And E is the same as what? I guess these distances here. That distance is 2, that distance is 1. So what's E? What vector is E? Yeah. It's just J, right? Yeah, it's 1J. It's just linked 1 in the Y direction. So E equals J. And F, what's F? I think the tip of it is up there on the right. Yeah. Negative I, although I think the length is it 2? Yeah. These look like the same length, but yeah, so negative 2I. Good. Good. All right. Okay, so just being able to sort of identify what these vectors are. It's a nice thing. Okay, and then about parallelness. So like 4, 5, 6. I'm not sure if all the groups got to this, but I think number 5, you can sort of tell like what the right thing to do is, right? Like what do you want to happen to make A, like in number 5, what do you want to happen to make A and B parallel? I think at least a few of the groups talked about this. Yeah.
Ratios of like D1 over W1.
Yeah, so you're, Okay, cool. So you're giving me the abstract thing. What's going on in this one? That's right. What are we multiplying by? Or what's the ratio? 3/2 or 2/3, depending on which way you're doing this, right? So 9/6. So like for number 5, for example, A is 6i minus 4j plus 8k. B is 9i minus 6j plus tk. And we have the ratio like 6/9 equals -4/-6 equals 8/t, like that. That's what you're saying? Make sure it's not B. Right, so somehow that should be, the ratio should be the same for the two vectors to be parallel, right? And so I think that means T is what, 12? So I guess I should write if A and B are parallel, then this should be true. Which means that should be true. Okay. And so in general, one way you could say this, I mean, some people, yeah, you could say the ratios. I think a few people in breakout rooms on Friday said something about like, if I multiply this by 1.5, and I multiply this by 1.5, I have to multiply this by 1.5. So that's a nice way to say it too, which is that like, I guess 6, like if we have V is V1I plus V2J plus V3K, and W, yeah, so I can say now what you were saying, that, so they're parallel if V1/W1 equals V2/W2 equals V3/W3. Another way to say that, though, the one thing we have to be a little careful with is the 0 vector. Well, I don't know. The 0 vector is just like 0i plus 0j plus 0k. It's like no arrow at all. It's just like a point. Sometimes when we're doing mathematical problems later, we're going to see that we want to include the 0 vector, even though like geometrically it doesn't really make sense to say it's parallel. So I don't like the idea that there's zeros on the bottom here. So you could say the same as V1 equals C times W1, V2 equals C times W2, V3 equals C times W3 for the same C value. Or really, just that V equals CW for some choice of constant C. So this is actually kind of the nice formulation, which is, this should make sense hopefully, which is two vectors are parallel if you can scale one to be the other, right? If I double the length or triple the length or something. And even notice C could be negative. I think I could say that too, like V and minus V, we would consider to be parallel, even though they point in opposite directions. So, yeah. C less than 0, okay. Sorry, not much room like that corner of the board. So, okay. Fair enough. Any questions about any of that? No? All right. Let's just look at page 2 briefly. So I suggested to look at section 13.3. I didn't have any homework assignment required, but yeah, the dot product of vectors. So one thing we're going to look at, we're actually going to look at 2 different ways to combine 2 vectors, to like multiply vectors, because we know how to add vectors, right? But there's actually kind of a way to multiply vectors, but there's 2 different ones. There's this one where you take 2 vectors and you get out a number. So this v dot w here is going to be a number. If you look at the next page, there's another product called the cross product. Sometimes this one is called the scalar product, and this one is called the vector product, just to keep in mind that like this, you actually take two vectors and combine them and get out another vector. And there's two different types of products. They're both useful for various reasons geometrically. Cross product is much stranger, and we'll get to that. We'll probably look at that on Wednesday. But the dot product is not too bad. It's just, you have your x, y, and z components of each vector, and all you do is like multiply the x components together, multiply the y components together, multiply the z components together, and add. Seems like kind of a random thing to do. It's not clear that that's going to give you a number that's interesting, right? I mean, it's something you can do with the numbers in two vectors, and the coefficients of two vectors. It's something you can do to combine them to get a number. It turns out though, and the book gives these two different definitions. It turns out there's this geometric definition, so the fact that they're the same is not obvious at all. The fact that they give the same result is not obvious at all. But you can also define it as the length of v times the length of w times the cosine of the angle in between them. And I mean the smaller angle, not the angle that you would get by going all the way around the outside, but the smaller angle. And so that's already interesting because, for example, you could use this to compute angles between vectors. Because if I know two vectors, I can compute both of these pretty easily. And then you get the cosine of the angle. So in three-dimensional space, you can get like the angle between two vectors pretty easily from this, which is pretty cool. And in general, it's just it's surprising that this kind of dumb thing of just like, oh, let's multiply the x components, y components, z components, add, is actually the same thing as like multiplying the lengths of the two vectors times the cosine of the angle between them. Okay. So what I'm going to do is have you guys go into groups and just start kind of working through these problems. So if you have a device, you might want to pull it up on the, I'll leave it up here, but if you might want to pull it up on the handout. It's on the handouts page, the vectors handout. Pull it up on your device, and yeah, so just some general, like just to play around with what the dot product actually is. Check some of the, just have you do a few. There's some basic properties you can convince yourself of. Showing that the algebraic geometric definitions give the same answer. Like if you apply the algebraic definition and the geometric definition to a specific dot product, you should get the same answer if they're the same. And yeah, actually, I think all the way on page like 5, there's like an argument for why the two dot products give the same thing using the law of cosines. But we'll come back to that. So what you guys can start on that, and then if you get to the cross product stuff, you can sort of read. You can try to read the top of the next page, and it's definitely strange, but you can start to just play with it. Okay. So groups. How are we going to put you guys into groups? Breakout rooms, it's easy. I press a button. Boom. How did we do it last semester? I did birthdays. Like line up by birthday and then put you into groups that way, or line up by where you're from, or line up by your favorite fruit in alphabetical order or something. I don't know, it's kind of fun to mix it up a little bit. Do you want to meet your birthday buddies? Let's okay, so what we're doing is we're going to line up here January through December, and I'll put you guys into groups and send you the boards. It's kind of random, but that's just one way I found to sort of randomly put people in groups. Some point in the semester, I'll probably just let you guys pick your groups. January down there on this by me, December. See if anybody has the same birthday. There's like a greater than 50% probability that two people have the same birthday. January is in here. Are you January? Oh, so your birthday was recently. Two people have the same birthday? All right. Yeah, there's this crazy thing that as soon as you have like 20 people, there's a bigger than 50% chance. All right. Januaries. Who are my Januaries? Same birthday? January 8th?
Yeah.
Wow. You're the 4th? February 5th?
February 11th.
So there's some, I might have to mix some Januaries and Februaries. I hope that's okay. You four can work here. Oh, geez, this is kind of, maybe here and these two boards. Your February, you said 5th?
11th.
11th?
23rd.
Oh, you were the 5th, 23rd. Oh, wait, what's today? Today's the 7th? Hey, happy, you were the 5th?
January 8th.
Oh, no, who was the 5th of February? Oh, happy birthday 2 days ago. And happy birthday Thursday? Wait, Friday.
Yeah, yeah.
Friday, all right. Oh, yeah, I can't do math. Okay. All right, so you said you were,
On March 7th. On March 5th.
all right, so you four go to the board back in the corner, the left corner there on the sidewall. What's your birthday? March 8th?
April 8th.
Oh, so you two are the same. Okay, birthday buddies. I need to start doing this in a way where there's enough room for everyone. Maybe the back left board. All right, what are we at? April something?
April 12th, May 5th, May 25th.
Wait, is that the third pair of birthday buddies we've had? Oh my God. Okay, you guys at the back center. What did you say, May 25th? My brother's the 26th.
June 11th.
July? Just July?
Oh, July.
Okay. Yeah, why don't you four go to that back right board? Hi, what's your birthday?
August 6th.
On the 7th. We're one day off. Oh, you're the only August. Okay. We're 29th. We're 23rd.
October 16th.
Oh, you're first. So you four go to this board. And oh, I have 5 left. I thought I had 4 left. I miscounted. You want to be a group of 5? When's your birthday?
December 8th.
You got off somehow from the rest.
December 27th. December 31st. December 29th.
Okay, you guys here. All right, so remember, introduce yourselves to your, especially your birthday buddies. I'm sure you want to know your names. And a couple things about group work, by the way, just before we get really started. What I would like you to do is kind of alternate who's writing on the board. I would like someone to be writing on the board so you can like see what other groups nearby are doing, and I can see what people are doing. But switch it off so that other people, each person can write stuff down, so one person's not writing on the board the whole time, so you all get a chance to write stuff down in your notes, because you might want to write down answers in your notes. And then just be nice to each other. You're a team, work together. I have called out student for being an asshole before, who just like was racing off trying to do every problem and show how smart they were. And I was like, you're being an asshole, like this in front of the whole class. And when he graduated, he was the first year, and when he graduated as a senior, we had a good laugh about it. I'm not sure he was so happy the day that it happened. But so don't make me call you an asshole. That's all. All right. With that note, get to work. I'll walk around. Oh. And sorry if you're on, and I'll stop the recording here. And if you're on, I'll try to watch the chat, Bo. And if you have questions, but just feel free to work through. Yeah, just work through the problems and I'll watch the chat to see if you have any questions. All right, let me stop recording. Stop or pause.